Quantum gravity is a field of theoretical physics that attempts to reconcile the principles of quantum mechanics, which govern the behavior of particles on a very small scale, with the principles of general relativity, which describe the behavior of gravity on a large scale. Gravity is the force that governs the behavior of massive objects, like planets and stars, and is described by Einstein's theory of general relativity. Quantum mechanics, on the other hand, describes the behavior of subatomic particles and the fundamental forces that govern their interactions. The problem is that the principles of general relativity and quantum mechanics are fundamentally incompatible with each other, making it difficult to develop a unified theory of both gravity and the other fundamental forces. This has led to the search for a theory of quantum gravity that can reconcile these two theories. There are several approaches to developing a theory of quantum gravity, including string theory, loop quantum gravity, and causal dynamical triangulation. Each of these approaches has its own strengths and weaknesses, and there is still much debate and research being done in the field. One of the key challenges in developing a theory of quantum gravity is that the very nature of space and time may be fundamentally different on a quantum level than on a macroscopic level. For example, in quantum mechanics, particles can exist in multiple locations at once, whereas in general relativity, space and time are treated as continuous and smooth. Despite the challenges, the development of a theory of quantum gravity could have profound implications for our understanding of the universe, from the behavior of black holes to the nature of dark matter and dark energy. Loop quantum gravity, LQG, is one of the approaches to developing a theory of quantum gravity. It is a non-perturbative, background-independent approach that attempts to quantize the geometry of spacetime by treating it as a discrete network of interconnected loops. The basic idea of LQG is that the geometry of spacetime is quantized at the Planck scale, which is the smallest scale at which the properties of spacetime can be reliably predicted. This means that spacetime is not continuous, but instead is composed of discrete atoms of space and time, which are called spin networks. In LQG, the fundamental entities are not particles or fields, but rather geometric structures called connections and loops. Connections describe how space and time are curved, while loops are a mathematical representation of the geometry of spacetime. The theory is based on the mathematical framework of gauge theory and uses the tools of algebraic topology to describe the geometry of spacetime. This allows LQG to make precise predictions about the behavior of spacetime, including the properties of black holes and the nature of quantum fluctuations. One of the key features of LQG is the concept of spin foam, which is a mathematical representation of the quantum fluctuations of spacetime. Spin foam describes the way in which the geometry of spacetime evolves over time, and it is used to calculate the probability amplitudes for different quantum states of the system. While LQG is still a developing theory and there are many challenges to be overcome, it has already provided important insights into the nature of spacetime and the behavior of gravity on the smallest scales. It is also an active area of research, with ongoing efforts to refine and extend the theory, and to test its predictions through experiments and observations. Loop quantum gravity, LQG, is a mathematically complex theory that poses many challenges to physicists and mathematicians alike. Here are some of the key challenges and mathematical concepts involved in LQG. Background independence is a key concept in loop quantum gravity, LQG, and refers to the idea that the theory should not rely on any pre-existing geometric or physical structures. Instead, the theory seeks to develop a description of the geometry of spacetime that is self-contained, and does not require any external reference frame or background structure to define it. The concept of background independence arises from the fact that spacetime is not a fixed or predetermined structure, but rather is a dynamic and evolving entity. According to the principles of general relativity, the geometry of spacetime is intimately connected to the distribution of matter and energy within it. This means that the geometry of spacetime is not fixed or predetermined, but is instead constantly changing in response to the distribution of matter and energy. In order to develop a theory of quantum gravity, it is therefore necessary to find a way to describe the geometry of spacetime without relying on any pre-existing geometric or physical structures. This is where the concept of background independence comes in. In LQG, the approach to background independence is to treat spacetime as a discrete network of interconnected loops, rather than as a continuous, smooth manifold. This means that spacetime is not described by a fixed metric or curvature tensor, but rather by a network of interconnected loops that describe the connectivity of spacetime. The advantage of this approach is that it allows the theory to be formulated in a way that is independent of any pre-existing background structure. Because the loops that make up spacetime are defined purely in terms of their connectivity, they can be defined independently of any external reference frame or background structure. This approach to background independence has important implications for the development of a theory of quantum gravity, because it allows the theory to be formulated in a way that is compatible with the principles of quantum mechanics. Because the theory is formulated in terms of discrete, quantized structures, it can be described using the language of quantum mechanics, rather than the more classical language of general relativity. In summary, background independence is a key concept in LQG, and refers to the idea that the theory should not rely on any pre-existing geometric or physical structures. This concept is important for developing a theory of quantum gravity that is compatible with the principles of quantum mechanics, and allows the theory to be formulated in a way that is self-contained and independent of any external reference frame or background structure. Spin networks are another key concept in loop quantum gravity, LQG. They are a mathematical tool used to describe the discrete, quantized structure of spacetime in LQG. Spin networks are based on the idea that the geometry of spacetime can be described as a network of interconnected nodes and links. The nodes represent the fundamental building blocks of space, and the links represent the relationships between them. In LQG, the nodes are represented by points, and the links are represented by lines or edges that connect the points. In addition to their geometric interpretation, spin networks also have a mathematical interpretation in terms of the representation theory of Lie groups. Specifically, spin networks are based on the representation theory of the group SU, which is a mathematical group that describes the symmetry properties of certain physical systems. In the context of LQG, spin networks are used to describe the quantum states of the gravitational field. Each spin network represents a particular quantum state of the gravitational field, and the dynamics of the field are described by the evolution of these states over time. The states of the gravitational field are described by assigning a spin to each link in the network. This spin represents the angular momentum associated with the gravitational field at that particular link. The spins are then combined in a specific way to define the overall quantum state of the gravitational field. One of the key advantages of spin networks is that they provide a discrete, combinatorial way of describing the geometry of spacetime. This makes them particularly well suited for the development of a theory of quantum gravity, which requires a discrete, quantized description of spacetime. In addition, spin networks also have a close relationship to other mathematical structures, such as spin foam models and loop quantum cosmology. This allows researchers to explore the connections between different areas of quantum gravity research, and to develop a more comprehensive understanding of the nature of spacetime at the quantum level. In summary, spin networks are a key concept in loop quantum gravity, and provide a discrete, combinatorial way of describing the geometry of spacetime at the quantum level. They are based on the representation theory of the group SU, and are used to describe the quantum states of the gravitational field. Spin networks have important implications for the development of a theory of quantum gravity, and are a valuable tool for exploring the nature of spacetime at the quantum level. The concept of the quantization of geometry is another key aspect of loop quantum gravity, LQG. It refers to the idea that the geometry of spacetime is fundamentally discrete and quantized at the smallest scales, and cannot be described using a continuous, smooth manifold. According to the principles of general relativity, the geometry of spacetime is intimately connected to the distribution of matter and energy within it. This means that the geometry of spacetime is not fixed or predetermined, but is instead constantly changing in response to the distribution of matter and energy. However, when we try to apply the principles of quantum mechanics to the geometry of spacetime, we run into a fundamental problem. In quantum mechanics, physical quantities are quantized, which means that they can only take on discrete values. This is in contrast to classical mechanics, where physical quantities can take on any value within a continuous range. When we try to apply this concept of quantization to the geometry of spacetime, we find that it is not compatible with the continuous, smooth geometry of general relativity. Instead, the geometry of spacetime must be quantized in order to be compatible with the principles of quantum mechanics. In loop quantum gravity, the approach to quantizing geometry is to treat spacetime as a discrete network of interconnected loops. The lengths of these loops are then quantized, which means that they can only take on discrete values. This discrete, quantized geometry is then used to describe the structure of spacetime at the quantum level. The quantization of geometry has important implications for the nature of spacetime at the quantum level. It suggests that at the smallest scales, spacetime is not a continuous, smooth manifold, but rather is a discrete, quantized network of interconnected loops. This has important implications for the behavior of matter and energy at the quantum level, and may lead to new insights into the nature of spacetime and the fundamental structure of the universe. However, the concept of the quantization of geometry also presents significant challenges for the development of a complete theory of quantum gravity. One of the key challenges is how to reconcile the discrete, quantized structure of spacetime at the smallest scales with the continuous, smooth geometry of general relativity at larger scales. In summary, the concept of the quantization of geometry is a key aspect of loop quantum gravity, and refers to the idea that the geometry of spacetime is fundamentally discrete and quantized at the smallest scales. This concept has important implications for the behavior of matter and energy at the quantum level, but also presents significant challenges for the development of a complete theory of quantum gravity. Another key concept in loop quantum gravity, LQG, is the idea of background independence. This refers to the principle that the laws of physics should be independent of any fixed background geometry, and should instead be expressed purely in terms of the dynamics of matter and energy within spacetime. In classical physics, the laws of physics are typically expressed in terms of a fixed background geometry, which is assumed to be unaffected by the presence of matter and energy. For example, in Newtonian mechanics, the laws of motion are expressed in terms of a fixed, absolute space and time. However, in general relativity, the geometry of spacetime is not fixed, but is instead constantly changing in response to the distribution of matter and energy. This means that the laws of physics in general relativity must be expressed in terms of the dynamic relationship between matter and energy and the geometry of spacetime. In loop quantum gravity, the concept of background independence is taken even further. The theory aims to provide a completely background-independent description of the gravitational field, which does not rely on any fixed background geometry or spacetime manifold. This is achieved by expressing the dynamics of the gravitational field in terms of the relationships between the fundamental building blocks of spacetime, such as the spin networks described earlier. These building blocks are not fixed in any particular background geometry, but instead represent the fundamental structure of spacetime itself. The idea of background independence has important implications for the development of a theory of quantum gravity. It suggests that any complete theory of quantum gravity must be capable of describing the dynamics of the gravitational field in a way that is completely independent of any fixed background geometry or spacetime manifold. However, achieving this goal is not without its challenges. One of the key challenges is how to reconcile the concept of background independence with the principles of quantum mechanics. In quantum mechanics, physical quantities are typically defined relative to a fixed background geometry, which is assumed to be unaffected by the presence of matter and energy. This presents a challenge for achieving a completely background-independent description of the gravitational field at the quantum level. In summary, the concept of background independence is a key concept in loop quantum gravity, and refers to the principle that the laws of physics should be independent of any fixed background geometry or spacetime manifold. This concept has important implications for the development of a theory of quantum gravity, but also presents significant challenges for reconciling the principles of quantum mechanics with the dynamic, constantly changing geometry of spacetime in general relativity.